All right, so this video is going to be on related rates. And when we think of rates, we automatically should think about derivatives because derivatives are rates. Now, prior to this, what we have been finding is dy dx, which is going to be a single rate. And when we talk about related rates, rates being plural, we're going to be having more than one rate within a particular problem, and we're going to be looking at how they are related to each other or how they interact with each other throughout the problem. These are some general strategies that you can use for working through some of the problems. First thing is just read the problem in the entirety and just make sure you have a good understanding of what's happening in the problem. Secondly, you're going to develop a mathematical model of the situation. Simply means draw a picture if a picture is warranted for this particular problem. Next, you're going to write an equation for the situation. Sometimes that equation might be a geometry formula like a volume or area or Pythagorean theorem or something like that. Then you're going to differentiate both sides of your equation with respect to time, t. And then substitute values for inequalities that depend upon time, and then interpret your solution. Make sure your solution makes sense in the context of the problem. All right, so you can pause video and read through those a little bit more detail if you'd like. Let's go ahead and start working a problem here. One of the most common types of problems used to introduce this concept of related rates is going to be the ubiquitous ladder problem. And so with this ladder problem, what we've got is a wall right here, and this white line is going to represent our ladder. The ladder is leaning against the wall, and what's going to happen is this ladder is going to start to slide away from the wall. Now, as the ladder slides away from the wall, the top of the ladder is also going to slide down the wall. Now, the ladder is going to slide away from the wall at a constant rate. But when the ladder slides down the wall, it does not slide down at a constant rate. That rate is going to change depending upon where in this process it is. The rate of this ladder actually coming down the wall actually increases as you come down the wall. All right, so reading the problem here, a 13-foot ladder is leaning against the wall. When the base starts to slide away from the wall, by the time the base of the ladder is 12 feet away from the wall, the base of the ladder is moving at a rate of 5 feet per second. All right, so let's go ahead and attach some variables to this problem here. We're going to let the base of this right triangle be x because Horizontal distance is usually an x value. Vertical distance is a y value typically. And I'm going to refer to this white line as z, keeping in order with the alphabet here. So now, if we want to think about a formula that relates the three sides of this triangle together, that formula would be your Pythagorean theorem, where x squared plus y squared would equal z squared. So that formula relates these three sides together. Now, at this point, once we have drawn our model, we came up with an equation that relates the measurements. Any measurement that is going to stay constant throughout the problem, we can substitute that value into this equation at this time. Well, if we think about this length right here, because the ladder is sliding away from the wall, this length is going to be changing. We cannot substitute this value into our problem. This value, the length of this, is going to be changing also because the ladder is going to be sliding down the wall. So we cannot substitute this value in. This is the length of our ladder. The length of the ladder does not change. So therefore, we can substitute the length of the ladder, which is 13 feet, into our problem in place of z. That will give us x squared plus y squared equals 13 squared, which is 169. So after we substitute values that are constant throughout the problem into our equation, we can now differentiate. So differentiating the left side with respect to t, time, you are going to get 2x dx dt plus 2y dy dt, and the derivative of 169 is 0. Now we're going to substitute values that we know into our problem. Well, we know the x value from up here is when the ladder is 12 feet away from the wall, so the x value is 12. Dx dt is the rate at which the ladder is sliding away from the wall. That's how x is changing. And that is a 5 feet per second measurement. So you're going to have 2 times 12 times 5 plus 2. Now, we have a value for x. We have a value for z. They did not give us a value for y. At this moment in time, when x is 12 and z is 13, we can, however, figure out what y is by using Pythagorean theorem of y squared plus 12 squared equals 13 squared, and then solving for y, which will give us a y value of 5. And then we have times dy dt is equal to 0, and dy dt is what we are looking for because it asks us how fast is the ladder moving down the wall. The ladder moving down the wall means that our y value is changing, and dy dt means the rate at which the y value changes with respect to time. That's what we're looking for. All right, so then going ahead and evaluating this, you're going to have 120 plus 10 dy dt is equal to 0. Subtracting 120 and then dividing by t is going to give us dy dt is equal to negative 12. And the unit of measurement on this is change in y over change in time. And the change in y is measured in feet. The change in time is measured in seconds. All right, so then part B of this problem asks, at what rate is the area Okay, so what rate is the area of the triangle formed by the ladder, the wall, and the ground changing at the same time? Now, on this, we're trying to find the rate at which area is changing, which means we're looking for dA dt. If we're looking for dA dt, that means we need a formula with area. And the area of a triangle is 1/2 times base times height, where base on this is x and the height is y. So if we differentiate, dA dt would equal 1/2, product rule here, x times dy dt plus y times dx dt, where x is 12, dy dt is negative 12, y was 5, and dx dt was also 5. And this is 1/2 times all of this. And so this is going to give us a half of negative 144 plus 25, which is negative 119 over 2. And this is change in area, which is square feet per second. So on the next problem, we have air being pumped into a spherical balloon at a rate of 20 cubic inches per minute. 20 cubic inches per minute is a change in volume. It's the rate in which the volume is changing. So that would be a dV dt measurement. And then the question is, how fast is the radius of the balloon increasing when the radius is 6? How fast is the radius of the balloon increasing? Okay, so that is going to be the rate at which the radius is changing. That is what we are looking for. Since dV dt is given to us, we need a volume formula for a sphere, which is 4/3 pi r cubed, differentiating both sides with respect to time. Now remember that 4/3 pi, that is your coefficient. Pi is a constant. So when you differentiate this, it's just power rule. Bringing the 3 to the front will cancel with the third, giving us 4 pi r squared times dr dt, which is the chain rule part of this. Substituting in, we get 20 equals 4 pi times the radius, which is 6 squared, times dr dt. So solving for dr dt, you're going to get 20 over 4 pi times 4 pi times 36, where the 20 and the 4 will reduce, giving us a final answer of 5 over 36 pi. And this is a change in radius with respect to time, which would be inches per minute for this particular problem. All right, so the next problem is going to state here that a conical water tank with vertex down has a radius of 10 feet at the top. So 10 feet is the radius of the cone and is 24 feet high. So the height of the cone is 24 feet. If water flows out of the tank at a rate of 20 cubic feet per minute, how fast is the depth of the water decreasing when the water is 16 feet deep? All right, so when the water is 16 feet deep, The question is, how fast is the depth of the water decreasing? So what we are looking for is dH dt. How fast is the rate of the water, the height of the water changing? All right, well, with this, we are given 20 cubic feet per minute. That is a volume, and it's a rate of which the volume is changing. So that is our dV dt measurement, which means we need a volume of a cone formula. The volume of a cone is 1/3 pi r squared times h. All right. Now, other measurements that we are given, we have the cone has a radius of 10. The cone has a height of 24. And the question is when the water is 16 feet deep. So the height of the water is 16 feet. Now let's think about this problem for a second. If we are to differentiate this problem right here, we would end up with dV dt over here, which we know that measurement is 20. When you take the derivative over here, you're going to have an r in the problem. You're going to have an h in the problem. You are also going to have a dr dt and a dH dt. We do not have dH dt. That's what we're looking for, so it's okay to have that in the problem. But we do not know dr dt, which means we would have more than one unknown in this problem if we were to differentiate this problem as is. That's a problem because you cannot solve an equation with more than one unknown. Now, this radius does not represent the radius of the cone. We're looking at the rate at which the volume of the water is changing. So this radius needs to be the radius of the water, and this height needs to be the height of the water. Well, the height of the water is okay, we know that, but we don't know the radius of the water yet. Now we can apply some geometry here to what we know. If we think about this right triangle over here, we know the height of the cone is 24. We know the height of the water is 16. We know the radius of the cone is 10. And so we can figure out the radius of the water at any particular time. Now, we also cannot put the 16 in here quite yet because the height of the water is actually going to be changing throughout the problem. So we're going to leave that as just an H. Now, these are going to form similar right triangles. And from geometry, we have a proportion that works with this where R over 10 is equal to H over 24. Now, let's go back to our problem up here. We need to find dH dt, which means we need to keep H in our problem. We do not have an R value or dr dt, and so we need to get the R out of the problem. Well, let's find out then what R is equal in terms of H. So if we cross multiply, that is going to give us 24R is equal to 10H. Dividing by 24 gives us 10 over 24H, which we can reduce to 5 over 12H. And that's what R equals, not H. All right, so what we can then do is when we see r, we can replace it with that 5/12 h. And then we have to square that value because it's r squared. Now, just doing a little simplifying here, this is going to be pi over 3 times 25 over 144 h cubed. Now, when we differentiate both sides of our equation, you're going to get dv dt is equal to 25 pi over 144 h squared times dh dt. All right, well, we know some values here. We know dv dt is 20 equals 25 pi over 144. We know the height of the water is 16. So 16 squared is 256 times dh dt. And then you can solve for dh dt, which is 9 over 20 pi. And it's the rate at which the height of the water is changing, so that would be feet per minute. All right, so on this particular problem, it says the volume of a spherical hot air balloon expands as the air inside is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. The table above gives selected values of the rate of change, r prime of t, of the radius of the balloon between 0 and 12. The radius of the balloon is 30 feet when t is 5. And the volume of a sphere is given by this formula. It says find the rate of change of the volume, which means we are going to be looking for dv dt, which would equal 4 pi r squared dr dt. And dv dt is the value we're looking for, which means we need to plug in some values. One is for r, and this says the radius of the balloon is 30 feet when t is 5, and so that is going to be 30 squared times dr dt. dr dt is the same thing as r prime of t, and at t is 5, which is the time in question, r prime of t is 2. So that's the value we put in here. And so just working this out, you're going to have 900 times 4 is 3600 times 2 would be 7200. Change in volume, and this is measured, so this is going to be cubic feet per minute, and that's it. On this one, the radius of a circle is increasing at a constant rate, 0.2 meters per second. What is the rate of increase in the area of the circle? So we need an area of the circle formula, which is pi r squared. If we differentiate with respect to time, you get dA dt equals 2 pi r times dr dt. The rate of increase of the area is what we're looking for, and so that would equal 2 times pi times the radius. Let me back this up for a minute. The radius was not actually given to us. What was given to us is the circumference is 20 pi meters. Well, 2 pi r is circumference. So that value is going to be 20 pi. The rate at which the radius is changing is this right here, 0.2. Oh, 0.2 is equal to 2/10. So I'm just going to replace that with the fraction here, and 2/10 because the 10 and the 20 will cancel, and that's going to give us 4 pi. This is the rate at which the area is changing, and that's going to be square meters per second. All right, next one, a camera is mounted 3,000 feet from the Space Shuttle launch. So we've got a camera down here. The camera needs to pivot as the shuttle is launched and needs to keep the shuttle in focus. If the shuttle is rising vertically at 800 feet per second, so that would be a DH DT measurement. When it is 4,000 feet high, so that would be our H value. How fast is the camera to shuttle distance changing? All right, so if we have a triangle here, and let's call this Z, that distance is what we are looking for at the rate at which that is changing. That's the value in question here. Now, if we call this X and this, H here, we know that X is 3,000 feet away from the launch pad. We can use Pythagorean theorem to find Z. Z at this moment in time, if you do Pythagorean theorem with 3,000 and 4,000, you're going to end up with 5,000, 3, 4, 5 triangle. And so now think about an equation that relates these would be Pythagorean theorem. So you have x squared plus h squared equals z squared. The x is not changing, so we can substitute that value in here. So you're going to have 3,000 squared. There's no need to actually square it because when we take a derivative, it's going to go away. All right, so now taking the derivative, you're going to have 2h dh dt equals 2z dz dt. Substitute values that we know. H is 4,000. dH dt is 800. Z was 5,000. And dz dt is what we are looking for. So you can divide. You have 2 times 4,000 times 800 divided by 2 times 5,000 equals dz dt. I kept it in those forms so that we can reduce. The 2's cancel, 4 and 5. And then 5 goes into 800. Let's see. 130, 160 times. And 4 times 160 is going to be 640. And this measurement is going to be in feet per second.